Greetings. My name is Bill Scamrock, and in this Advanced Research WRF tutorial lecture, I will be discussing idealized cases that are available in the latest WRF release. Idealized cases differ from the real data cases that most researchers use in WRF applications. Specifically, the idealized cases utilize simplified geometry, such as 2D or 3D Cartesian boxes, and simplified atmospheric physics configurations to capture some essential elements of specific atmospheric phenomena. We provide these idealized cases for a variety of purposes, including as a mechanism to test the solver over a broad range of space and time scales, from LES scales of a few meters and a few seconds to large-scale phenomena of using mesh spaces of hundreds of kilometers and time steps of several minutes. These test cases also reproduce some known solutions, so it allows us to test the solver in this way, in that we know what the solutions look like, either from analytic solutions we have, from converged numerical solutions, or from comparison with other models. In terms of what's perhaps most important to users, these cases provide a starting point for other idealized experiments, and these idealized cases that I'll be talking about have been the basis for numerous papers that are in the literature today. They can also be used to test physics development in a very idealized and simplified setting. So if you want to focus on a particular physics component, for example, microphysics, one can look at just simple clouds, for example. And finally, these are tests that are the easiest to run for testing the solver. The initial atmospheric state in these idealized cases is typically analytic, and the formula are contained within initialization modules. One doesn't have to bring in external data nor run the WRF preprocessing system to build and run these idealized cases. And also, given the idealized geometry and configurations, not all the post-processing practices can accept the idealized simulation results. The simulation results that you'll see in the talk that's coming were generated with NCL scripts available as part of the release. So everything in the initial download of WRF, the initial fork of the repository, has what is needed to build and run the test cases, and then just pulling a few of the post-processing packages and scripts will allow you to look at the results. When you clone the WRF GitHub release, the idealized test case configuration files for running the cases are found in the test directory off of the main WRF directory. The initialization code that creates the initial conditions file for the WRF simulation sits in the dyne_em directory, same directory that contains the Advanced Research WRF solver code. And of course, the physics sits in a different directory again. Here are the idealized test cases in the WRF release. In red are the paths to the directories containing the configuration files for each case. For example, the nameless.input file, along with a README file that explains what the test case is, has references to the literature for that test case, etc. The directory name starts with the acronym of dynamical core, in this case for the Advanced Research WRF, or Eulerian Mass, followed by the name of the test case, and in the 2D test cases, followed by a horizontal direction, X or Y, which denotes the horizontal direction that is active in the test case, and in the storage arrays in WRF and what you'll find for the output. There are 1D, one spatial dimension, vertical test cases, 2D, which is a horizontal and a vertical dimension, and 3-dimensional test cases. In the following slides, we're going to look in detail at the Hill 2D test case, and we'll present results and specific configuration notes for some of the other test cases that are available in this release. The initialization for the Hill 2D_X case is contained in the dyne_em directory in the file module_initialize_ideal.f. This file contains not only the initialization code for this test case, but for most, but not all, of the idealized test cases. The files needed to run the test case after you build WRF and the initialization are found in the em_hill2d_x directory that sits inside the test directory off of the main WRF directory. To build and run the hill2d test case, you run configure in the main WRF directory as you would for building the real data version of WRF. Compile em_hill2d_x, the command you would give to build this test case after you've configured the build itself, builds two executables, the ARW model, WRF.exe, and an executable called Ideal.exe. Ideal.exe produces the initial conditions, much like Real.exe produces them for the real data configuration of WRF. But here, Ideal.exe will not need any external data to be brought in. The WRF model, WRF.exe, is the same WRF model used in all applications. It doesn't have any test case compile time specific code in it. Ideal.exe, however, is specific to the specific test case that you compile. In this example, the em_hill2d_x test. Here's a plot that's produced from an NCL script for the hill2d_x test case. What you're looking at is the contour of temperatures, our color contour. You can see the color contours down below. And the vertical velocity are the black line contours. And this is a classic mountain wave case over a very small mountain, so small that you can't see it in the contour plot as deforming that lower boundary. It's essentially reproducing the linear solution. There's a mean flow of 10 meters per second going from left to right in the domain, and when it encounters the mountain, produces the wave. This is a classic solution and very close to the linear analytic solution. So this is what you'll see when you go through that process of building, running, and then plotting the results for this test case. The code producing the initial state for the hill2d_x test case is found within module initialize ideal.f. Everything needed to produce that initialization is contained within that code. Model levels are set in that code to produce a stretched eta coordinate, which is nearly equally spaced z, or one could go inside the code and modify it to produce the equally spaced eta coordinates. The terrain is set in that code. That code reads a single sounding from an ASCII file that is inside of the run directory for that test case, and that ASCII file has the name import_sounding, and that sounding is interpolated to the grid vertically in every column. An equation of state and hydrostatic balance is used to compute the full thermodynamic state in the model. The wind fields are also interpolated to model levels. All of this is done within this initialization routine. An important point here is that WRF always uses a three-dimensional grid, even in the 2D test cases, which may be XZ or YZ. The third dimension, the one that's not used in the 2D test cases, has only 5 planes, and the solution will be identical on each plane. We do this because putting the logic into the WRF solver to run purely 2D would just litter the code with all kinds of conditionals looking for these specific cases. So we've decided to run fully 3D, but only a few planes in that third dimension, which doesn't vary. As I mentioned earlier, these test cases can serve as a starting off point for other idealized test cases. For example, if you wanted to change the mountain shape in this 2D test case, one could go into the module initialize ideal.f and look for the code for the hill2dx case that sets the terrain. And this is what you'll find in that module. And you can change the mountain shape by changing the formula for the variable ht that you see indicated here, where it sets the height field and then is used to set the lower boundary condition for the geopotential, which is a variable within ARW. For example, you can make the mountain three-dimensional by adding a dependence on the J direction. That's one of the loop indices here, and probably increasing the number of J points on the mesh. That's how we do it when we want to do a three-dimensional mountain simulation inside of ARW. Input soundings are used for a number of the idealized test cases, and these soundings are read in from an ASCII file. You can edit any standard editor. That file, here for the EM quarter SS test case, is structured as follows. The first line contains 3 real values: the surface pressure in millibars or hectopascal, a surface potential temperature, and a surface water vapor mixing ratio in grams per kilogram. Each subsequent line contains a value in the sounding, starting with the height in meters, then the potential temperature at that height, the vapor mixing ratio at that height, and the U and V, west-east, north-south velocities in meters per second. And then as you go down the file, you're looking at progressively higher heights. Typically in these idealized simulations, the state is horizontally homogeneous, so this one sounding is used to initialize the entire domain, the entire idealized box that one has. And this state, while given in height, is interpolated to the Whorf eta levels as part of the initialization. Now, extrapolations occur if the model levels are above the top level given in the sounding file or below the bottom level. So make sure that your sounding extends high enough such that the top of the Whorf model grid is contained within that sounding, so it doesn't extrapolate off the top, and likewise for the bottom, so that you don't get any surprises in your initial state, because the Whorf initialization will not warn you if it's doing these extrapolations. Here are the results for the 2D squall line test case. This test case includes moisture and uses a simple warm rain microphysics, the Kessler microphysics. Vertical wind shear in the lowest 2.5 kilometers results in a tilting of the updraft and this classic squall line structure with a leading anvil and the beginnings of a trailing stratiform region. Many papers from the 1980s onward use this general 2D configuration to understand how squall lines develop. So you'll see a lot of these kinds of simulations in the literature and papers. For the squall 2D test case, you can run this in either X or Y. So there's actually 2 test cases, one with the underscore X, one with the underscore I. And they both produce the exact same solution, only the solution is in different coordinates here. The initialization code for both of these is, again, in the initialization module, and the thermodynamic soundings, which are identical, are found in the test directories. We use this to test the solver when we make changes to it, because these solutions should stay identical except for a rotation internally in terms of where they sit in the array space Whorf. Moving to smaller scales, the density current test case originated in the early 1990s and was used to compare dynamical solvers and atmospheric models. An initial cold bubble of air is centered in a domain that contains a neutral environment. The cold bubble, being denser than its surrounding air, descends to the surface, and gravity currents extend out in both directions, in the 2 horizontal directions. The eddy viscosity is fixed, so the solution can be converged by increasing the model resolution. Here are the results at the final time in this simulation for 4 different grid spacings. You can see the coarse grid, the solution looks not very well resolved compared to the finer grids that are shown in the upper panels. By the time we get to 50 meters, the solution is fairly well converged. You can still see some differences between 100 and 50, but those differences in the solutions are very, very small. All of these test cases can be run from nameless.input files that exist in that test subdirectory. So you can reproduce the results you see here. There are published solutions to this test case for many atmospheric models, usually in papers describing their formulations. However, WRF is by default configured with a turbulent Prandtl number of 1/3, while the gravity current test case uses a turbulent Prandtl number of 1. So if you want to reproduce the published results, then you have to change the Prandtl number that appears in the share subdirectory in WRF in the file module_model_constants.f. And then you need to recompile WRF, and then you can run the initialization in the test case and get the published results. Turning to convection, here's a depiction of a solution from an early height coordinate version of WRF for a 3D supercell thunderstorm. The low-level temperature field is color contoured in the lower boundary, on the lower boundary, and shows the cold air behind the storm and the warm, moist air in the environment around it. The shaded cloud water field shows a large leading anvil. These storms often produce tornadoes, and these idealized simulations of this nature are used in research applications today, and you'll still find numerous papers every year coming out that are based upon these kinds of simulations. The Eulerian mass version of WRF, which followed on from this height coordinate version model, reproduces this solution, and you can produce it yourself. Large eddy simulation applications refer to those that resolve the largest eddies in the turbulent atmospheric flow. More technically, they're resolving the inertial subrange in the kinetic energy spectrum. In the atmosphere, LES more generally refers to simulations using grid spaces of a few hundred meters or less, although the grid spacing needed to resolve the largest eddies and the kinetic energy inertial subrange is problem dependent. The LES test case in the WRF release is for a free convective boundary layer where the heating of the lower surface drives turbulent motions and boundary layer growth. This case is found in the test_EMLES directory, and the initialization is in the main initialization file in the dyne_EM directory. All the information you need to run this case is provided, and this test case is one of those that appears in a paper by Chin-Ho Moing et al. In 2007 Monthly Weather Review. Here are the results from this LES test case. The domain is doubly periodic in the horizontal, meaning what goes out the right boundary comes in the left boundary, and similarly for the top and bottom boundaries in this horizontal cross-section depiction here. The top panels show the temperature and the vertical velocity perturbations at a given time, with narrow, strong, warm updrafts and wide regions of weak, cool, subsiding air evident in the two plots. The lower plots show the classic structure of the convective boundary layer with the horizontal mean potential temperature and the horizontally average velocity variance plotted as a function of height. These types of LES simulations, with the addition of moisture, wind shear, surface inhomogeneities, etc., form the basis for a large area in the research world in atmospheric sciences today, and you can use this configuration as a starting off point for other configurations that you may want to use for LES type simulations. Another very active area of research in the atmospheric sciences today is centered around tropical cyclones. In this idealized case, an initial weak vortex develops into a hurricane over a course of several days. The Cartesian box is large, 3,000 by 3,000 kilometers, and the test case is primarily used for testing physics and environmental modifications, at least at this resolution that you're seeing here of 15 kilometers. Depicted in this plot on this slide is the initial vortex structure. It's axisymmetric, so a simple two-dimensional plot gives you that complete structure. And the humidity is color contoured, and the azimuthal velocity is in the line contours in this figure as shown. So this is the initial state at time 0. On top of this, a small perturbation will be added to the initialization, and then this vortex will slowly develop convection and strengthen into a tropical cyclone. Here are plots showing the color contoured wind speed at 10 meters and the line contoured radar reflectivity at simulation days 1, 3, and 5. You can see that at day 1, there's just convection all around the center of the vortex, extending fairly far out. By day 3, the vortex has contracted and strengthened quite a bit, with strong convection around the center here and just a few cells in the far parts of the field, but significantly stronger winds. And day 5, we have a very strong tropical cyclone centered in the domain. There's no banded structure in this particular simulation because there's no radiative effects in this configuration which would bring about the banding. So one can use this type of simulation to look at different environments or to look at other physics, etc. And this is why we provide it. The final test case we'll look at involves the simulation of a baroclinic wave in a periodic channel. The horizontal boundary conditions in this channel are periodic in the x direction, meaning what goes out the right side comes in the left side in this depiction you're seeing here. And there are rigid walls in the north and the south. The domain is large, 4,000 by 8,000 kilometers. So you're seeing here the full extent in X, and you're seeing about 6,000 kilometers plotted in Y. So you're not seeing where the walls are, but the flow is very quiescent by the walls. The initialization is an unstable baroclinic jet that has no variation in the X direction, but a perturbation is placed on top of that jet to produce the classic baroclinic wave that forms over the space of several days. Depicted in the plots here are the solutions at day 4 and 5. We're looking at the low-level temperature fields with the warm air depicted in the red colors, the warm colors, and the cold air in the blue colors, the darker colors. We're also seeing the wind vectors and a 3D depiction of the cloud fields, which is transparent or partially transparent. Fairly clear, you can see the classic cold front, warm front structure, and by day 5, that warm core seclusion is very obvious in these plots. As noted earlier, the initialization code is in module initialize_ideal.f. However, the two-dimensional jet structure is read from a binary input file that's part of the release that's there. And the initial perturbation is hardwired in the initialization code. So you have much less latitude to change parameters in this particular test case. Specifically, if you look at the default configuration, it's set for this 4,000 by 8,000 by 16 kilometer depth channel. You can run it either dry or moist. You will get a baroclinic wave in the dry case. And in the moisture case, the structure of the wave doesn't change very much, but some details of it will. And you turn on moisture by setting any of the microphysics options in WRF to turn on a microphysics. The initialization will see that a microphysics was on, and it will initialize the water vapor that then will be lifted as the baroclinic wave develops in the fronts form and produce the clouds and precipitation fields that you saw in the previous figure. As noted, the initial jet structure is part of the release that's provided in a binary file, and it only works for 81 grid points in the north-south direction and with a horizontal mesh spacing in that north-south direction of 100 kilometers. If you want to use other configurations of that test case, some researchers have in the past developed initialization code for other jets that can be used with WRF, for example, using different potential vorticity structure in that unstable jet. So if you want to do other initialized jets, you can either build the initialization code yourself, or you can ask us who you might contact to find code that other researchers might be willing to share with you for doing this inside of WRF. So if you want to learn more about the test cases, I would suggest you look in the README files that are sitting inside the test case subdirectories, and they are in the test case and the test case name where the nameless.input files are. So read those first if you want to know a little bit more. Most of them contain some references to literature, which I think you'll find very helpful if you're not that familiar with these specific test cases. And again, the initialization code and any initialization code associated with the idealized test cases is found in the dyne_em directory. As noted earlier, most of the test cases use initialization code found in module initialize ideal.f. The bottom 4 test cases in this list use different initialization code that resides in the indicated module files. So if you want to make changes for those bottom 4 test cases, you have to go into this different initialization code and compile that. If during the course of your research you have any questions about any of these test cases, you can pose these questions to the WRF MPAS forum, and we'll answer them as best we can. If you develop new idealized cases that you believe would be useful to the community, please feel free to contact us and we can discuss the possibility of a pull request to incorporate these new test cases into a future release in our GitHub repository. I hope this tutorial lecture was helpful to you, and thank you for your time and attention.